Hello, everyone. Welcome to today's AI Let's Talk. And today, I'm very pleased to have Xuan Liu from UCSD to give a presentation about her most recent work, HumanStudy-Bench, or AI agent design for participant simulation. And I'm today's host, I'm Da Wei. Let me first give a brief presentation about Xuan Liu's background. So Xuan is a first-year PhD student at the University of California, San Diego, advised by Hao Jianxing. Her research focuses on AI and human-computer interaction, or human-like intelligence in LLM or VLM agents, and developing AI tools to accelerate scientific research and studying privacy and security issues in AI. Her work has been published in top AI and HCI venues, including iClear, Europe's CLI, and Triple AI. Her first author paper just received the CLI 2026 Best Paper Award. And I'm today's host, I'm Da Wei. I'm currently a second-year PhD student at Arizona State University, and my research just focuses on large model and data mining. Now, Xuan, so it's your time to give a presentation about your work.
Okay, hi everyone. Thanks for having me today at Nice Talk, and I will just share my screen. So today I want to talk about something that's been bugging me. When people use LLM to run psychology experiments instead of recruiting humans, does AI actually behave like a human? And if not, what can we do about it? That's basically what HumanStudy-Bench is about. But first, let me just quickly introduce myself. Actually, Da Wei has just helped me to introduce me, so I will just quickly put this part. I'm currently a first-year PhD student at UC San Diego, and I'm really interested in the overlap between AI and social science. Like, do LLMs think the way we think? And can they be irrational the way humans are? And can we actually use them to run experiments? That's basically the three things I'm working on: understanding AI behaviors, building AI tools for social scientists, and also some work on AI safety and privacy. So here is the bigger picture of what I've been working on. The idea is pretty simple. Like, social science gives us really well-designed experiments for understanding behavior. And we can use those same experiments to understand the AI too. For example, Cogmira is my first work in this field. And we basically ask, do large language model agents show same kinds of irrational social behavior that humans do? Things like prosocial bias, cognitive bias, that sort of things. And that was a paper published at iClear last year. And then it's about the Cobra. So if this bias exists, can we actually control them? Like, deliberately dial up or down to a specific bias. Turns on you can across prompts, activation steering, and fine-tuning. That one just got a best paper, and which is very exciting. And this is really where reproducibility and controllability come in. Cobra shows that these AI behaviors aren't just random noise. They are reproducible across models and experience. And more importantly, they're controllable. You can precisely specify a target bias level and steer the agents there. And how HumanStudy-Bench, what is today's focus? This takes reproducibility and controllability even further. We take real published human studies, reconstruct them as a test bed, and ask, can AI agents actually replicate what humans did? If you can reproduce human experimental results with AI agents, that's a much stronger claim about both the fidelity of these agents and our ability to evaluate them rigorously. So it's explore, control, and evaluate. 3 projects, 1 story. So let's zoom in today's part, the evaluation part. Okay, so why are we doing this? There's been tons of hypes about using LLMs to replace human participants. And honestly, the promise is amazing, right? when we run a 1,000-person study in 5 minutes instead of 5 months. And early results looks pretty great. There are many papers out there shows that models seems to make human-like decisions in economics, marketing, psychology experiments. But here's the thing. This kind of things is kind of messy right now. Like if we change a few words in your prompt, and you can get totally different results. And also, if you change the temperature or sampling size, you will get different results too. And the bigger problem is people keep saying like GPT can do these experiments without separating what models can do from how you set it up. So our take is this isn't just which model is the best questions. It's an agent design questions, like how you wrap the model, the persona, the instructions, the demographics, and all those kind of social science experimental setup. That matters just as much as the model itself. And we need to evaluate all of this properly at the level of actual scientific conclusion, not just the individual answers. And this is how we begin to do the HumanStudy-Bench, and that's motivate me to commit to AI and social science. So here's a key idea. It's super simple equations, but really important. Agents equals to base models plus specification. So when you use LLM like GPT to run a psychology experiments, you're not just using GPT. You're using GPT plus whatever you told it. For example, you're 25 years old college students, or act like a human participant, or maybe you give it a whole background stories, that stuff, the role framing, the demographics, and the background. That's the specification. And here's the punchline. That specification is not neutral. It's basically a hypothesis about what makes the simulation human-like. If you change the specification, and you can get completely different experimental outcomes from the same model. We will see some really dramatic examples of this later. So this is why we frame the whole thing as an agent design problem instead of a model problem. Basically, we take real published human studies in HumanStudy-Bench, including those classic psychology and behavior economics experiments, and turn them into testbed that AI agents can run through. Then we compare, did the AI reach the same scientific conclusion as humans? Here are some quick numbers. We include 12 foundational studies here, and there are over 6,000 trials. And the original sample size ranging from 10 to over 2,000 people. And we measure the alignment with two metrics called PAS and X. So, which I will explain it later. And the whole thing is automatic and standardized, and this is important. And also the HumanStudy-Bench is open sources and extensible. If you have studies that you want to add it, you can. And we're actually looking for contributors from the communities. So what makes this difference? For me, I think there are 4 key features of HumanStudy-Bench. The first one is, as I just told, that we frame this as an agent design problem. Most existing benchmark test a model with one fixed prompt and call it a day. But that conflicts the base model's capabilities with the experimental setup. You can't tell if a bad result is because the model is bad or because of the experimental setup is not good enough. And we instead search across different agent specifications to find the best design for each model. So we are measuring best case performance, not some arbitrary configurations. And we'll see later that the agent design can swing performance by around like 35%. It matters a lot. And the second one is the high fidelity reconstruction. We don't write rough approximations of experiments. Our image replace the actual trail sequences, the exact participants' instructions, and run the original analyzed pipeline in a short runtime. Well, it turns statistical papers into reusable simulation environment. So When we say we are running the mirrogram experiments, we mean that the mirrogram experiments are not a paraphrase of it. And the third one is, this is the biggest one, like we do the inferential level evaluation. Existing metrics usually compare points estimates or distribution distance, but they ignore the randomness in human response and lack standardizations across paradigms. Well, we introduced two metrics. The first one passed, like probability alignment score, which measures whether a scientist would draw the same conclusion from agents' data as from human data, explicitly accounting for uncertainty in human baseline. And the second one is effect consistency score, which captures how closely agents reproduce the actual effect sites. So we're not asking, did the agent pick the right answer? We're asking, would you publish the same findings? And the last one is, this is standardized and extensible. The whole pipeline can inject new studies. It's not a frozen benchmark, and it's a living platform that keeps growing. So let's show you more about the pipeline. Here's our full pipeline. There are 4 stages, pretty intuitive. The first one is filter. We pick studies that actually have enough detail to reconstruct. And LLM will help us scan a paper about humans, and actually the humans makes the final call. The second stage is extract. We take the study and turn it into something a computer can run. For example, like the participant profile, experimental design, statistical tasks, run choose, basically a complete computational specification. The third one is the execution part. We actually run agents through the experiments. The same stimulus, the same condition, the same instructions as the original image study, and everything is standardized. And the last part is evaluate. We run the exact same statistical task or agent data and compare with humans. And then that's where our two metrics come in. The most cool things, I think, is all the things is totally modular. We swap model, change design, add studies, whatever, it's just a plug-in part. So here are something about the detail of the two metrics. As I just explained before, 2 different questions about these 2 metrics. The past probability alignment score resolve the agents reach the same scientific conclusion. Like if a human show a significant framing effect, does the agent also show it? This is a yes or no kind of things, but we make it smooth and continuous. And the effect consistency score, okay, even if the conclusion matches, is the actual idea or is the actual data similar? Are the effect size in the right ballpark? You can get the conclusion right, but have wildly different numbers. So we actually need both. For example, a high pass in a low X means you got the right answer, but the wrong numbers. And as we will see, that's actually super common. We can walk into each one in details. The pass in details, the formula looks fancy, but the idea is simple. It's the probability that human agents agree on hypothesis. For example, either both say yes, there is an effect, or both say no, nothing there. The clever part is we don't just use a hard p-value cutoff. You know that like p equals to 0.049 significant or just 0.051 not significant. That's super brittle. Instead, we convert things to smooth posterior probability through a sigmoid. So near misses get partial credit. This matters a lot in practical because like many effects sits right around the borderline. Like pass handles that gracefully, ranging from 0 to 1, where 1 is the perfect agreement. And the second one is X, is the other side of the coin. Well, pass asks the same conclusion, while X here asks the same numbers. It's a linear coordinate correlations. standardized effect size, there are two components here. The row captures whether the relative patterns of effect is right, and the C penalizes you if the magnitudes are off. Let me make this concrete with the false consensus studies. That study has 4 stories: supermarket, term paper, traffic tickets, and space program. Each produce a different consensus effect size. So the row asks, does the agent also show a stronger false consensus for the supermarket stories than the space program story? Is the ranking across conditions preserved? And the C asks, even if the agents get ranking right, are the actual effect size in the same ballpark? Or is the agents producing consensus effects that are, say, 3 times bigger across the board? We will need both to score well. And the spoiler alert is, like, most models do pretty badly here. They might get the conclusion roughly right, but actually effect size are all over the place. That's an important distinction. So, okay, we can show the actual study. Here are our 12 studies across 3 domains. I won't go through every single one, but let me give you a flavor. The first category is individual cognition. It's the classic one, like framing effect, representativeness of false consensus, and these are those stuff that won the Nobel Prize in economics. So it's very well established effects. And also we have strategic interactions. For example, those game theory studies, like prisoner dilemma, trust game, dictator game, beauty contest. And there are also about people corporations trust each other, share resources. And the last category is rather social psychology, things like north side effect and ash impression formation, like minimal group paradigm and drinking norms. This gets at how people form judgments and how they are influenced by social contexts, or carefully selected, like full materials available and clearly specify statistics, and there has strong replication evidence. These are some of the most robust findings in behavior science, which makes the term a great benchmark. So in the initial benchmark work, we test 4 agent design from the simple to complex. The first agent variation is the blank one. Just give the model the task, nothing else. And this is our baseline. And the second one is the role-playing one. We will just say that act as a human participant. This is what most people do right now. And the second one is the demographic one. You just tell the model you are a 22-year-old female college student or whatever match the original study participants. And the last one is the full backstory one. Well, it's the demographic information plus personality, life history, daily routine, something like that. Basically a whole character sheet. We run all 4 across 10 models and plus a mixed model baseline. So that say is in total 4 by 11 grid. Let's see what happened next. Here's a mini leaderboard, and we have the full results in our project website. We can see that on the main result table. I may want you guys to notice a few things. The first one is the Gemini 3 flash on the top, which has about 0.49. And that's the best results of all models. Basically, a coin flip on whether the agents agree with human conclusion. Not great, right? The result is actually not great. It even not over the 0.5. For different models prefers different design. Look at the best methods column. Something like A3 is the demography one. Some like the A4 is the background story one. And the GPT OSS 20B actually does best with A1. A1 means that we didn't prompt anything to the model. No specification at all. That's already interesting. So also notice the X column, the universally terrible. The best one is 0.2, even when they are getting the conclusion right, the numbers are way off. And check out the bottom row, which is the mixed model. The pass is only 0.26, and it was the worst one. Using many models together is actually worse than any single model, which is very different. Like many people use multi-agents to do things. But currently in social simulation part, if we want to simulate a specific person or specific participants in social science studies, single model may be better than mixed model. And we'll talk about this later. So yeah, the state of things is honestly not great, but there is a lot of interesting structure in these results. Let me show you the visibility one. Here, if we see the p-value distribution of human agents, we may find that on the left, the human p-value seems sharp peak below 0.05. These are robust effects. Humans reliably produce significant results, but on the right side, the agents, see how spread out it is. Instead of a clear peak, the p-value are linking all over the non-significant range. Some trails work and some don't. This is a core problem. If you're a social scientist using these agents instead of real human, you'd draw a different conclusion. The replication just isn't reliable enough yet. And now, if we look at the picture of agent and human's effect size, we may find that if agents perfectly match humans, all these dots would be on the line. But they are not. The correlation is only 0.33, pretty weak. And look at the spread. Agency effects are all over the place compared to humans. They're overshoot and they're undershoot. Sometimes they flip the directions entirely. This really problematic part is like when human significant effects become non-significant for agents or vice versa. That means the opposite scientific conclusion from the same experiments happens in agents and human. That's why the X scores are so low. And this one is really interesting. If we look at these pictures, when we look task by task, like human are unimodal, as we can see on the yellow one. Like most tasks clustered near high alignment. This makes sense. And these are well-established effects. Because human are unimodal, so we can get our conclusion about human effects. But what about the agents? If we look at like the blue part, is bimodal. They either nail it, the pass near 1, or completely miss, and the pass near 0. So almost nothing is in the middle. It's like the model either gets the phenomenon or has no idea. There's no grace for degradation. So that's really different from how humans work. And it makes agents unpredictable as stands in for human participants. You cannot just tell that in advance which task they'll ace and which they'll bomb. So here is really interesting trade-off. Well, we can see in previous results, like the Gemini 3 Flash has the best pass for around 0.49, but has a terrible X at only 0.1, meaning it gets the right conclusion, but the effect size are way off. So flip side, the Mistral model has a low pass at around 0.2, but relatively better X. Gets the magnitude more right, but missing the significance. There's no model that's good at both. That's the basic tension. We have to decide what we care about more, the right conclusion or the right data when we are conducting the experiments. And again, on sample at the bottom with around 0.2 pass, mixed model doesn't really help. It makes things worse. More on that later. So this is one of the most surprising findings. More context does not always help. Something is hurt, like demography. Well, yes, almost always good. 9 out of 10 models improve with the demography part. That's solid. But the background stories on the top of demographies, the results is mixed. For Gemini and Mistral, it's actually make things worse. So more detail isn't automatically better. And what about the role play? If we ask the model to act as human, can actually hurt the performance, especially for Cloud and Mistral. It triggers this rationality bias. The model's idea of human is too perfect and consistent. Also, bigger models are always better. And the temperature tuning doesn't help. Here is the full grade. Every model, every design, a few things jump out. Like every agent is more dispersed than humans. Not one model gets that clean peak distributions. For example, like the A3 and A4, which means the demography and background story, do help tighten things up a bit, but there's still a big gap. And it's super model specific. Like the same design affects different models differently. No one size fits all. And this is why we need systematic benchmarking instead of just like trying stuff, exploring things. And here is the temperature scaling visualization. A natural question may come, like, can we just choose the temperature to fix this? We've tried temperature from 0.1 to 1, systematically ablation on the Mistral model. Well, the answer is no. If we look at these scalar points, each dot is one statistical task. We may see that the human p-value on the x-axis, the agent p-value on the y-axis, across all temperature, the patterns are nearly identical. Well, temperature does almost nothing. And that's actually an important insight. The gap isn't simply noise, it's structural. It's baked into how model represents this scenario, so don't waste time on temperature tuning. And also, we think that the real lever is about the agent design. So here are the 4 big takeaways of this study. The first one is, it's not about the model size. I know that everyone loves scaling narratives, but look at this, there are around over 35% performance variations for the same model, just different agent design. That's very huge. And the design matters way more than which models you pick. Gemini Flash with no context at demographies the way better. While the same model, and for the GPT OSS, if we use the 120 billion versions, this one actually does worse than those with 20 billion version. So the bigger model is literally worse here. So if we are picking a model for simulation, we may not just grab the biggest one. We may think about the design, like which kind of model we need and which kind of agent design we need and which kind of study we are using AI to simulate. Like different AI may suit different studies and different models may suit different kind of human behavior. And the second takeaway is there is no magic recipe. Like every model has a different sweet spot. Gemini wants demography, and that's the thing. Well, GPT-5 Nano may want the full background story. And what about Mistral? Mistral is extremely sensitive to role playing. Actually, the role playing destroys performance. So we cannot just follow the template, like always add demography. Always add demography doesn't work. Always add background story doesn't work. Always add the persona doesn't work. we just have to match the design to the model. And that's why systematic benchmark here we need is the only way to find how the model specific should be the best one. And the second takeaway, and this is my favorite one, we may ask that if we ask a model to act as human participants, we may think that it may help to the social simulation. This is just so intuitive, but it can actually make things worse. For example, like the GPT OSS does better with no persona. Then we ask the model to act as a human. And the Mistral, the role-playing caused a statistically significant drop for P less than 0.001. Telling it to be a human makes it less human-like. How ironic it is. Here's why we think this happened. The model's ideal human is the rational one, consistent one, and logical beings. But actually, what are the real human likes? We are kind of messy and irrational. We are biased, we are emotional, we are inconsistent. And that's exactly what these experiments are measured. The psychology experiments, social science experiments are measured the human irrationality. But the AI think all of the human is very rational and we are very smart. So when you are saying that, be human, the model activates its idealized version and actually overlooking the very biased part of us, which makes it more realistic. That's kind of wild. And the last takeaway is the mixing model doesn't help. This surprised us too. The logic seems sound, like different models, different bias, maybe they'll average out, right? But the answer is no. Well, the path of earning like 0.26 near the worst of everything. Mixing model cause destructive in each model, and each model has its own systematic bias. And when you blend them, the bias doesn't cancel, they compound. So we end up with data that's neither consistently like any one model nor like humans. And the bottom line is like, when well-designed agents beat a diverse ensemble every time. So let me just wrap all these things up. There are three big messages. Where the first one is an agent design problem that really matters in social simulations, not just the model evaluation problems. So how we set up the agents matters at least as much as which the model we are using. And the second one is the current alignment is honestly limited. It's not reproducible and it cannot be better controlled. So models are polarized. They either nail a task or completely miss it. No model is great, and there's no ensemble helps. And the third one is like design over scale. The work of it helps, but the background stories are hit or miss. Well, temperature sampling doesn't matter really. And also the reasoning or non-reasoning is not the most important. So the size also doesn't matter, which is turn back to our conclusion. The design does. Each agent's design may suit a types of or a range of human studies. Like some kind of agent design may very suit those individual cognition part, and some agent design may very suit for those kind of like game theory part. HumanStudy-Bench just give everyone a standardized way to test this stuff, and we are open source and growing. So speaking of which, what I would like to invite everyone to contribute here is, we've just opened up a contribute page in our project. Like if you have a published study and want to add to HumanStudy-Bench, here is how you can do. It's just a simple GitHub repo workflow. You just fork, branch, and add your studies files and run our verification script and submit it. The folder structure is pretty simple. Like only include the metadata, ground truth, participate specification, and stimulus. Also, you can include an evaluation script. We have templates for everything. And the study shapes work. For example, you can include those cognitive bias work, game theory work, like social psychology works, and whatever. And even the management part or finance work is okay. And if it has different kinds of outcomes and published data, it can go in. And there is a step-by-step tutorial in our website we can visit. Maybe I can go through here. Let me just check whether or not. Yeah. I'm not so sure. Can you see the here? Yeah, here is our page. You can see overview here, like overview and the full leaderboard. There are lots of results with different kinds of specifications, agent design, and different models, right? If you click here, you can see that the very detailed results of the whole 12 studies. Okay, let's hide this. And here are some simple card of each study. But we have the contribute now. If we click the contribute now, and then we can click the step-by-step tutorial. So here will be, here will be a very, very detailed tutorial, introduction of the big picture and how to extract data from a paper and how to build your own study files and how to submit your study. If we go back to paper, okay, not this one. We can see that this 12 study is our original one. We choose the classical one, which win the Nobel Prize, but we also need the modern one. Like one of our contributor is from the management, and he contribute the one that he think is the most popular study in his field. It's about cognitive process of entrepreneurship, because his research is literally about innovation and entrepreneurship and business, right? And if you're contribute to our benchmark, your name will show in here. Like actually your GitHub name will show in here, and also you can just like print your name in our website so everyone can see it. So that's it. That's how to and also like we consider for those people from social science, they are not so familiar with the GitHub part, so they can just submit the studies through our website. Like submit a zip file here is okay. All right, let's go back to our PowerPoint. So that's literally all about the HumanStudy-Bench. And I would like to also take this opportunity to give a brief introduction of the work. It's work around like you can specify the cognitive bias from 0 to 4 scale and adjust via the prompt activations or fine tuning until on the targets. And I think we can also go to the web page here. Yeah, this is the project page of Cobra. here are the Cobra in the action is the demo video. Like we can just specify the target cognitive bias level or behavior level at the left side. And through a very, very quantitative part, we can actually specify how the model will behave and how biased the model is, right? And here is an interactive introduction part. You can just click here to know how the whole system run and how the control is, and also how the cognitive bias index and all the past bad is become. And here are the cognitive bias we currently include. We include 4 cognitive bias. And this project is also welcome contributors. Like contributors can add more cognitive bias and different kinds of behavior here, and we will help them to control those kind of behavior in a quantitative way. Right. I think that's all about today's talk. So I'm welcome every questions, and if you are interested in all those kind of topics, you can just contact me through no matter email or just WeChat or just X. Yeah.
Yeah, thanks, Xuan, for this very interesting talk. And actually, it's very impressive to me to see you have a series of very related work, even you are just in your first year. Yeah, and I think we can have our Q&A session now, and we already collect some questions from our audience. And also, if you have any questions, please feel free to share it with us. I think the first question would be if the 2 metric PAS and ECS, are they orthogonal, which means they just measure, different aspect of the simulation performance, and how to measure if they are good enough to, let's say, use it for social simulation.
It actually measured the. Oh, let's go back to the slides. For the 2 metrics, actually answer 2 questions. Like the first one is the PAS actually measure the whether or not the scientific conclusion is the same. Like if we have a social science paper, the social science paper is evaluates the how human perform in that kind of phenomenon. So using the PAS, we are compare the results from human and the results from the agents, whether or not they can get the same conclusion. And the X is about, and the X about is the data distribution. For example, let's take a simple example, like in the human study paper, like we have different kinds of results for female and male. Like female may show more, for example, female may show more framing effects and male may show less framing effects. But actually, if we test it on the agents, if we we prompt the agents, like you pretend to be a female and another agents, you pretend to be a male. But actually the agent results is the male agents show more framing effects and the female agents show less framing effects, which means that the data distribution is not matched. And this is what X is measured, right? So all the 2 metrics is measuring how these agents can be the similar part as the human participants, the original human participants' performance in that specific studies, right?
Yeah. I think it's very clear. And my understanding for this question is maybe we can consider it from a distillation perspective. Because, for example, if we consider distillation, actually we also have sample level accuracy. For example, whether the label of that sample is correct. And also we have maybe outcome-based accuracy. let's say, what's the performance of the student, right? So I think there might be a trade-off, right, based on maybe how biased the result is. Yeah, so I think it's intuitive. Yeah, it's intuitive.
It's intuitive. Yeah.
And I think another question is, so basically in this paper you explore some limitation of, let's say, for example, spreading, or use different type of prompting or temperature to achieve a very good performance for nowadays social simulation, AI-based social simulation. So the question is how to achieve social simulation, given that nowadays technique is not maybe very good to achieve it, and maybe should we have some specialized training? Will it help us to achieve the AI-based social simulation?
So this part is like when I was conducting the benchmark of HumanStudy-Bench, I only tasked about the like the different variations of prompt one. Like we have like demography, just ask like role playing and blank and those kind of things. But actually,
Hey, Sean, could you hear me?
but about the related work, I just offline, right? I can re-answer the questions.
Sorry to interrupt.
I did.
There might be some network problem. Could you repeat the answer from the very beginning?
Oh, okay. So we currently, like, just like the paper's conclusion, like current technique is not enough for social simulation, right? We currently test only the simple version of role playing, background story, and persona things. But what we found is that in the related work, for example, the Cobra one, we can use the classical social science experiments as our answer to make a closed loop system to continuously target what we want. So in that way, or use that kind of methods, we can potentially achieve what we can in social simulation. For example, we, I think, let me just go back to the Cobra one. In HumanStudy-Bench, we only just we only adjust the prompt engineering part, is this part. But actually in Cobra, we adjust every space that we can in an LLM. The input space, activation space, and parameter space. Use different kinds of tactics that everybody knows. Like in activation space, we use representation engineering and activation steering. And in fine-tuning, and in parameter space, we use fine-tuning. So the problem is why we cannot reach the social simulation part using current technology is because that we don't have a answer, or we don't have a best metrics to fine-tuning the model or adjust the model to reach the answer. But in Cobra, like if we have an agent first, we put it in a classical social science experiments, and we get an answer of how the cognitive bias level is. And for example, we want these agents to have a very low cognitive bias. For example, like 6.6, 2.6. But actually, when we just put the agent in, we may get the answer of 4. So the magnitude of that cognitive bias may be the 4. And this is not what we want. So what we do is we use this all kinds of technologies, maybe prompt engineering, maybe representation, maybe fine-tuning, to change the model and change the agents. And then we go back to the agents, and agents go back to the task-based simulation. And then we measure again until the answer reach that exact 2.6. So from this closed loop system, we can just better control what we want the agent be like. So for that way, we can have a better social simulation for the agent parts, right?
Yeah, I find this very interesting. So basically, you try to explore this problem from three perspectives, right? Prompt engineering, representation engineering, and
Yeah,
fine
yeah,
tuning. So
yeah,
could
yeah,
you
yes.
briefly summarize the result you got here? So, for example, by steering which space or which technique, by applying which technique, you get the best result in AI-based simulation.
Yeah. So for the simulation, like cognitive bias, the representation engineering get better results because we want to control it very precisely. And the representation engineering, we make things at the activation space. It can be a little bit kind of linear part, but the prompt engineering not the well. Let's see. Maybe we can just go to the paper. Here are the results. Yeah. So if we can see that, okay, here is the what we test on reasoning and direct part. We can see that if we use the representation engineering, the reasoning, if the model we enable reasoning or we just directly put the model here, we may see that the two line is literally the same, which means that we can very better control how the model perform using representation engineering in those kind of social simulation part to control the agent behavior, right? And if you see we just use prompt one, it may kind of not so smoothly, right? And also, here's are the temperature ablation. Like this is the representation, but for the temperature, like I don't think temperature matters so much because no matter the representation one or the prompt numerical one, the lines are actually similar, which means that we have a like okay control for all of this, right?
Yeah, I find this funny very interesting to me because actually basically I think representation engineering is like kind of steering, right? It's not
It's steering,
you
right?
change the prompt or you just fine-tune a larger model a lot. It's basically a kind of steering. So can I interpret the result like, for example, for the pre-trained foundation model, they already have a lot of knowledge, a lot of this type of person. And what we do is just we try to steer it to the type of person we want it to mimic, or we want it to play the role.
Yeah, that's right. That's right. So yeah. So for the small because for this one we test like for open source model and for closed source model, like for rep engineering, representation engineering, we can only like apply it to the open source one. And when we test a very, very small model, it cannot work. And this one, the scale is very important. Like the small model, they don't even have the definition of what cognitive bias is. So it actually doesn't understand what cognitive bias is. Then it's very hard for us to steering it, right? And for larger model, it has a Yeah,
that makes sense. Yeah. I think we got another question about the Cobra paper. And the question is basically how do you adjust I think it's a hyperparameter, right, when you do the fine tuning, and also how user interact with the model.
Yeah, like we currently let's go back here. So I'm currently sharing the whole screen with the paper, right? You can see paper here.
Yeah, I have seen the paper.
Oh, okay. So I'm sharing the okay. So here we go back to the project page. Like, let's go back to this closed loop system. For Cobra, we are currently the first step is we put the raw agent in the test bed and we got results about how it performed in cognitive bias. And perhaps it's about like the magnitude is we develop a cognitive bias index. Just we use something similar to the a scale, right? Like and we calculate for the cognitive bias index, and if it not match, we will use steering vectors to make it match, right? like currently, like for example, we just add a weight here. If the original one is the weight is 4, if the results is larger, and that is not what we want. We want a smaller result. We just make the weight a little bit smaller, and how do you say? Yeah. So how the user interact is we test all the things for automatically add the weight or deduce the weight, and we have a form, and we store the form in the database. So if we want a full magnitude for cognitive bias index, we actually check our form because we already do the experiments, and the form gave us the weight, and we add that, and we like multiply the weight on the steering vector directions, and we can got the right results, right?
Yeah, I think it makes sense. I got it. And if you're interested in maybe more details, right, you can refer to Xuan's this Cobra paper.
Yeah.
And let me see. All right, I think we don't have any other question from our server platform, and maybe I can ask one last question. So, in the paper, in the HumanStudy-Bench paper, basically you explore maybe nowadays larger model still don't have the ability to to do the maybe simulation, right? So I think there are something similar in the larger model training or larger model development area that people want to build such type of user simulator, right? To maybe based on the feedback, based on the response and the question, the user simulator is able to give a response. For example, whether the user is satisfactory with the response, right? And do you think maybe the conclusion in the social simulation area could be transferred to the area I mentioned, that the user simulator area in larger model development, and maybe how to improve this type of user simulator for larger model training? Maybe how can we borrow some insights from the paper?
I think the results of the HumanStudy-Bench on social simulation can partially just transfer to the user simulation. But the difference is that the HumanStudy-Bench currently focusing on the human participants in social science studies, which means that we may have a ground truth. But I'm not so sure whether current user simulator has a ground truth. So we cannot, I think it's hard for us to validate whether or not the results is okay or not. But we may have some insights from it, right?
Let's see. I think there might be some gap, but for the at least the pattern, how you build the platform and how you transfer the existing result to the verifiable environment. I think that's something that we borrow from to develop better user simulator. All right. Go ahead.
And the user simulator, I think maybe we can do user study and to get the ground truth. Right.
Of course.
So and we do user study and we got ground truth, and we use the data to train the model and to fine tune the model, or we just use representation engineering. Right.
I agree. I think there are a lot of resources we can get online. Without the survey, maybe we can get to use model training. Thanks again to this very interesting talk, and I think that's it for our talk today. And thanks for watching.
Okay.